We are here in the ECEPE project, which is the ECQA certified powertrain engineer. We are talking about the element 3 e-motor control of the unit 3 system engineering of electric powertrains. Here in the room we have the two partners who developed this training module, which is ISCN. I am from ICN, Richard Messnerz. My colleague is from ICN, Damien Eckert. He is not here today, but he collaborated on the material. And the partner with us is TU Graz. And what you see here is Georg Macher from TU Graz and our researcher Maximilian Brunner from TU Graz. What is this training module about? It is about e-motor control. And for that purpose, we have acquired a motor toolkit. What you see in front of us is such a motor toolkit. Some basic elements of it are visible. So we have here a motor control unit with a processor on it where all these calculations are running and the motor control is calculated with a display. And also which is then actuating phase currents. And to actuate the phase currents, it needs an inverter board, which is here the lower board. And this inverter board, you see here three big capacitors, but you see very little pieces beside the capacitors. And these are small switches which allow to set the PWM, which is a certain percentage of a voltage and current load on coils. Coils are placed in such an e-motor in a 120-degree angle shift, so you can think it like a circle, and then we have it 0, 120 and 240, so in 120 degree difference you place the coils and you can put currents on those coils, and by that you produce a magnetic field, and the magnetic field can drive the rotor. And inside the motor you have this rotor. This is the piece that looks out from the motor, and the rotor is turning because we put this magnetic force on the rotor. The rotor itself is also a permanent magnet which is reacting on those magnetic loads and fields what we actuate by putting the phase currents on the coils. That's the basic setup. Also in the basic setup we have some sensors that are built into this system so that we can measure back the currents and we can calculate the position of the rotor. Now I would like to hand over to Georg. He will explain us a few words about the basics of such a brushless DC motor, which we have as an example as a motor kit, and some basics how it works.
Yeah, so I will give you some. You will see also the animation there of the three half bridges that we have there as a control for the motor. That is connected, as Richard said. Inside there is the rotor with the permanent magnets, and depending on the switching positions of the different half bridges, so you can consider them as like real switches that are turning off and on and off again. It will be that the rotor is located to the external, to the stator magnetic field, and depending on the magnetic positioning, it will be driven to the next position. So it will go from one step to the next. So we will have 6 different positions. So every 60 degree, we will have a position where the rotor will align with the magnetic field in the stator there. So it will be a stepwise circulation around that we will be able to produce in this regard. As I said, stepwise, that's not really the smooth approach. So it will be really a harsh one. Which go very stepwise in this regard, but there will be some approach that we can take to smoothen this a little bit. And Richard, I think that is something that you can explain in more details there.
Yeah. Okay. So like Georg explained, we would not just jump every 60 degrees around around the circle, but we would be able to look at each specific angle position of the rotor and actuate the rotor accordingly to where the rotor is standing with a concrete, very detailed angle position. And to do that, we use space vector PWM strategy. A space vector means, like you can see here on the slide, that we have here the three phase currents. They are named here U, V, and W. You see on the left upper screen that the U, V, and W can be positive and negative, depending on if you use the high or the low switch to actuate the phase currents on the half bridges. And there are some principles how we control such a motor. One principle is, for instance, that the sum of the three phase currents is 0. And you can see that also here in the example that U is minus, W is minus, and V is plus. And when you add these three, it's 0. Also, when it's minus, it only means that we have a different direction of the current, or we changed actually north or south pole, what you have seen before when the coils have changed the color. And we do that, we change the direction by actuating a negative instead of a positive current. And we do that by actuating the either high or low switch of this half bridge. And the phase currents in the space vector control, like you see in the picture, are set by knowing the rotor position and what phase current we need, so that the magnetic field forces push and drag the rotor further on. And this is developed in form of algorithms inside the motor control. So we would always know the rotor position and then actuate the correct phase current, so drag the rotor further. And like Georg explained before, we would not do it per 60 degrees, but we would know even by a 360-degree angle every degree separately and know in detail what to actuate. So we get a more smooth control. And now I hand over to Maximilian, who explains how that works then in practice, because that's the theoretical model, but in practice we have to implement it. So maybe a few words to continue now for Maximilian. Yeah.
So the main problem is, as Georg described, we have 6 switching positions that we can use for our software. So we have to develop some algorithm to use the 6 switching positions and generate out of this, for example, 360 positions that we need to smoothly control the motor. Mm-hmm. So the trick is we take 2 neighboring vectors. So I define the 6 positions as 6 vectors. We take 2 neighboring vectors and switch them with weighted time components. So for example, 40% of the time there's vector 1, and on 60% of the time is vector 2. So it's exactly 40% from the angle between the 2 vectors. So we drive slowly from one to the next, and so we have a smooth operation. And therefore it's called PWM, because we quickly change between these vectors. So for the motor, it's resulting in one analog, so to speak, mean value of the 2 vectors.
Mm-hmm. Good. We can see that also that in this kind of circle, which is on the left upper corner, is it below the half bridge? We have another representation of the circle, and this kind of PWM strategy is displayed by these green curves inside that, right?
Yeah, right. These are the PWM duty cycles for each phase, mm-hmm, displayed there. And you see that only one phase changes its values per sector. Mm-hmm. That can be used later when implementing the software, that you don't need to calculate the whole vector, because 2 of the 3 components are staying the same for one sector.
Mm-hmm. Okay, yeah. And then I think, Maximilian, you wanted to explain us also a little bit about this motor control modules interacting with the power electronics. Yeah?
So here you can see a depiction of the whole device and software and hardware components. We get the PWM signals from the space vector modulation as described before, and feed that to the power electronics. So the switches which were mentioned on the second board with the capacitors, and these switches are actuated by the signal in a very fast manner, in our case 20 kilohertz, and drive the motor with some kind of sinusoidal signal. Then the motor turns, and we measure the rotor position of the position of the rotor, and use that to calculate for once, with help of Clark and Bach transformation, we will explain that later, some stationary currents or virtual currents, because they are just mathematical, that are controlled by the torque, which is the current control regulator. The currents are define the torque, and then the circle continues by back transformating new set points, and then feeding in the space vector modulation block that again generates the BVM signals.
Mm-hmm.
So, and then there is the second loop for when we want to control the velocity of the motor,
Mm-hmm.
because with the inner loop, as described before, we can just control the currents of the motor and therefore the torque. But we want, for example, have a constant RPM rate.
Mm-hmm.
And then we need the outer control loop with measuring of the velocity of the motor and regulating this.
Mm-hmm.
So the inner control loop, Maximilian, is controlling what? That would be, where would I be as a driver with my accelerator pedal?
As a driver, the accelerator pedal would be the IQ set point marked in the diagram. So this would be some value, for example, 40% of the torque.
Mm-hmm.
That torque is then controlled by the inner loop. It's so that the torque is independent of the speed of the motor.
Mm-hmm.
We don't want to be dependent on the RPMs of the motor. We just want, for example, in a drivetrain, 50 Newton meters, and independent as from the start up until the load reaches it. And
I think that's, sorry to jump in, but that's a good factor. As a driver, you want to increase the newtons that you have, or irrelevant if you are going with 1000 RPMs or 2000 RPMs, you just want to go for it. You want to increase the speed.
Exactly.
And that's, you need more torque. So basically you are changing the torque request.
Yeah, I cannot just set a voltage, because it would very rough behavior of the motor, because the current is relevant for the torque, but the current is also very dependent on the RPM, and therefore a little bit of voltage would make huge torque from standstill, but very little afterwards.
Yeah.
So to have a smooth and controllable behavior, we want to control the current, and that's the inner loop.
Yeah. So let's one thing to summarize is, therefore the set point is more or less the gas pedal, and I have a specific, when I keep the same gas pedal, I have a specific torque. Yeah. But if I drive with fixed gas pedal up a hill, then I normally as a driver would have to press the gas pedal more to keep the speed. And for that one, I need the velocity regulator.
Exactly. The velocity regulator is then the automatic cruise control.
Right. And then we have here the ID and IQ. The one is the current, the other one is the torque here. Yeah.
Both are currents, but the ID current is in direction of the rotor, and the IQ current is 90 degrees to the direction of the rotor, and therefore generates torque. The ID does not generate torque and normally is controlled to 0.
Yeah. Okay.
But you can use it in rare cases, for example, to smooth the operation.
Yeah, okay. Because one of these two I can use to identify what torque I have achieved. Yeah. And important is that in the control we always need a rotor position, And just to understand Clark-Park transformation, why do we need that? Maybe a few words about that, because why do we need the Clark-Park transformation, which simplifies more or less the mathematics?
It very much simplifies the regulation of the currents, because the core principle is we want to control the magnitude of the currents. And because it's a three-phase system, we need to control three amplitudes, 120 degrees separated, and it's not an easy task. Therefore, we use a mathematical transformation. In principle, we use two mathematical transformations, the Clark and the Park. The Clark transforms into a Cartesian coordinate system, as the three-dimensional or the three vector system of the motor, into a two-dimensional Cartesian coordinate system. And the Park transformation just rotates this coordinate system with the angle of the rotor, and therefore we get two constant values, one Q and one D. Park.
Which is then why we have ID and Q here. Yeah,
exactly.
And where would we find details about the transformation? I think that's a pretty standard algorithm, which you can find anywhere. Yeah, and it's programmed in software inside this motor control unit. Yeah.
Exactly.
Okay, and then interesting is, why do we need the inverse Park transformation? Because we at the end need, again, instead of two values, we need the space vector with three values, right?
Exactly. Yeah. We need the space vector for the three phases that we can transform into the BWM signals for the electronics.
Okay. Yeah. So I think this gives us the setting here, right? And
from my perspective, I already steer towards the hardware. So I heard now was very interesting, some background, some theory background, but I'm very keen on the hardware. So I think the next thing is to
wait, but we are soon there, and now we can, maybe we should start with experiments, do you think?
I think we should really go for some experiments.
I cannot hold Georg back anymore, he wants to experiment, okay? Yeah. So we are starting now with experiment 1 and 2 together, where we are setting specific frequencies on the motor, and a few more words on the experiment by Georg now, and then Maximilian will explain us the details. Okay.
Yeah. So as we can see in the depiction also, we will start simply, or we will very simply. So let's start. I think you run the program, you will explain a few things, and I will then be there to touch it.
Okay.
Yeah.
So at first we want just to set a fixed frequency and fixed voltage signal to the motor and see what happens. Of course we want to use our setup here, and therefore we just ignore the lower three blocks and just use the top line and set some fixed modulation inputs, MD and MQ, which represents the voltage of the outputs, and the rotor position is simulated by a constant running timer counter, and so just nothing is measured and just output is generated as sinusoidal signal.
So we are flashing now the software with that kind of variant on the controller. So we usually have here a development computer with the software on it. What Maximilian is doing is flashing the code now on the controller, and like here, only those areas which are active are marked on the experiment 1 or 2. Yeah.
So we start with a fixed frequency for 300 RPM of the motor.
Okay.
And then some medium voltage, nothing important, and just flash it. And
Now comes my important part. Huh?
so,
Yeah.
Jörg, you can
What
start.
we have seen is maybe also that is important, it went one time round. So it is actually initializing the position to be able to measure the position. Yeah. So it's like every motor has this kind of calibration or first startup calibration phase. Yeah.
Yeah, not every motor, but our model uses an incremental sensor, so we don't know the position on start and need to just turn around slowly one electrical round, and then we know the position and zero the sensor.
Yeah, right. So if you would use more expensive sensors, yeah,
Like a resolver.
We would know the angle position by sinus, cosinus and could calculate it. Yeah.
Then we don't need the initialization.
Then not.
Initialization.
So,
Okay.
question.
Now your finger, you can start.
Question.
Start.
Gentlemen, ready?
Yeah.
So let's start. Oh, exciting. Yes.
Yeah.
But not racing. Can we
Up.
make more? Can we make more fun of it?
So it seems to operate normally. You can see it's quite some power, and
Okay.
let us try 2000 RPM.
So take care, we are jumping to a very high value, 2000. Okay.
Question: What could go wrong?
Do you think it will turn immediately very quickly for you so that we have a high RPM? What do you think? So let's try out. Yeah.
Ready to race?
Yeah, ready to race. Yeah.
Okay, that is
Disappointing.
It's like my mobile phone when it's ringing and I have put it to silence. Huh?
yeah. That's a bit disappointing. I saw it didn't really move. So just vibrations, like you said, like with the mobile. So Maximilian, what went wrong? What's the issue here?
Yeah, the issue is the rotor has some inertia, and we need to accelerate the rotor in half an round of the magnetic field.
Mm-hmm.
So because if we reach 180 degrees angle of the stator field to the rotor field, the torque turns in the other direction, because the magnets are in the other direction, the north and south pole, and then of course all acceleration is reverted, and it's just accelerating in the wrong direction again. And yeah, if we select a too high frequency of the stator field, the rotor cannot accelerate fast enough, and therefore just vibrates.
So that reminds me at the story of the donkey. Yeah. So with the donkey, where you have on a stick the carrot in front, and then he will follow that. And then if you turn left, then he will turn left, and if you turn right, he will turn right. But if you just rotate too fast, he will simply not know what to do.
Exactly, it's the same problem. Yeah.
So our donkey does not move. What can we do against that? What would be the next proposal?
Yeah, I would propose to just slowly increase the frequency of the field, and then the rotor should follow the rotation.
Yeah, so we are starting next experiment, yeah, where we would not just jump to the frequency, but we go step by step higher.
Exactly, yeah. We have prepared this as a whole mode of the software.
So again, you see it's actually motor control software. He's using the laptop, he's flashing the new source code in, yeah, compiled of course, and then a compiled code in.
Mm-hmm.
Maybe for the practice, you always need the right compiler for the right motor, because the compiler what he's using is depending on the chip which is on the controller.
Mm-hmm.
Because the software must run on that controller. That is why he has to use a specific laptop and development environment, right?
Exactly, yeah. So we just say start with 300 RPM, as we said, that works.
Very
in the
good.
first try, and then slowly increase the speed until 200. So we've set this in software, and up it goes.
Yeah, we have to wait until it's flashed.
Yeah.
Okay. I think Georg.
Now it's
Ready
again
to go.
racing time.
Yeah.
So again
Yeah.
my time. Okay.
No, even if it's a high RPM, it reaches the high RPM. Hey
now,
guys.
Now we can achieve it.
Very
so we
good.
see it's still vibrating.
So if you stop with the hand, it's still vibrating. Yeah. Why is that?
Now we have an issue, yeah?
Yeah. That's the problem, because we don't measure the rotor position. The controller doesn't know that the motor is stopped, and it's the same problem as before. If we lose the rotor, there's no coming back to the speed.
And now comes the space vector control, because we would know the rotor position. We would always know where we can start from there again to speed up the rotor, and therefore we could reach the speed again. In experiment 3, we should add now that we use the rotor position, right?
Exactly.
So please adjust the software, recompile the software, flash the software, but now we use the rotor position. Because if we use that and we go step by step higher, then even if we touch it, we should not lose anymore the rotation, the RPM.
But we don't have any fixed RPM now. We just set the voltage, and also and align it so that it's fully 90 degrees to the angle of the rotor, and therefore the maximum torque.
So if it slows down, then it will continue again, or?
It will continue, as the stator current is always set in the right angle, but we don't have any fixed speed anymore. Before we had fixed speed for loads until it loses the rotor, but for some loads it was exactly the same speed.
Okay.
Yeah. And now it should be flashed.
It should be flashed. I didn't check it. Okay, so it's ready.
Yeah, ready to go. Yeah.
Ready.
Because now you can try to stop, but it should speed up again. Yeah.
Okay, I can stop it.
And now?
Then it starts again.
Yeah. So
Great.
it starts again. Because
Okay.
it knows now the position. Yeah.
Yes.
But still you could slow it down. You've seen that.
I could slow it down.
So you have no hot finger.
No.
Yeah.
That went well.
Yeah, we could improve. We could increase the voltage and
Okay,
the maximum.
then.
But the next experiment is even more sophisticated, as we can control the actual torque or the current, and with the current the torque is set.
Right, and so if you have the current and the torque is set, so even if it tries to slow down, it will have the power.
Yeah, it will have the same torque for every RPM value and for every position.
But that will be our next experiment then.
Yeah. So let's try out this experiment. I think it's this one here. Yeah, the experiment number 4. And in experiment number 4, let's try that out. Now we are with experiment 4, and we increase now the functionality of the motor so that we can set the specific current. So maybe a few words by Georg about this.
I have to do more work in this context. So, so the more we experience, the more I have to also put on in the enter in the device. Yeah, with that experiment, we're having a constant torque, but the experts just interrupt me if I do something wrong. But there will be the engine or the motor. As soon as I turn it on, it will give me constant torque, and if I give some load, it will constantly increase the speed. Only if I overcome the torque that I have there.
So the torque is constant for for every speed of the motor and not depending on the frequency, like with the voltage control.
So this means it would continue endlessly with the...
It would continue, but it does have some air resistance and
some safety for the device
safety,
itself.
But yeah,
I cannot ruin it. That's
you
good.
cannot ruin it now.
Yeah. Okay. So let us start a few things. And yeah, the motor turns and it will continue. I have a low torque in this regards and I can simply hold it. Yeah.
And it will return to a constant torque again.
And it will speed up, or it will get, now it continue to speed up and will get faster if that's okay. So we will increase a bit the torque, so that we also see that it will.
And even then.
And then I have quite more force to stop it.
Yeah, but it will again return to a constant torque what we have set as a set point. Yeah. For the constant. Yeah. So it means we can keep a constant speed. Yeah. Velocity regulator will be then the next phase. Yeah.
So
but a few words more, maybe for Maximilian.
Maximilian, that would be the normal operation mode in a vehicle, or?
That would be the normal mode for manual gas pedal setting. But the next mode would be to control the velocity, so to speak, to have an automated cruise control. That would be the next step. But now it's just I give, for example, 50% of the throttle and have 50% of the available torque for each speed of the motor.
Yeah. So what I do is basically I'm the hill in this regard.
You're the hill, yeah, and the gas pedal is on the display.
Yeah. Or your finger is the gas pedal. Yeah. When you increase, then it's your gas pedal.
So the finger is optional. Or a gas pedal. Okay. Yeah.
And then we have seen that we need to achieve that. We need not only the voltage, but we need also the current control. And this is now included when you look at the picture, when we have also the torque regulator included.
Exactly. It's utilizing the whole inner loop, so to speak.
Yeah.
And then we have the outer loop in the next experiment.
Yeah. So and for those participating, also just remember we have the laptop with the software. We have here the controller on which the software is running. And every block which Maximilian is showing here is like a software component inside the software control. So when we would open the software box, then all of that, what is on the left side in the picture with software, is in reality a software component, having those algorithms which are written on the box. Okay, so I would say
up to the next.
Okay, now we are at the last experiment where we have the full functionality of the e-motor and work, and it's called the velocity regulator. And Georg will say a few words and then our researcher will explain more detail.
Should I say some few words? Okay.
Sure.
Again, you interrupt if I do something, if I don't explain it in too details. But basically that's the full setup. Now we have the full-blown setup with also the adaptive cruise control. And now the motor that we have there would accelerate no matter how much force I would be providing against it. So it would be accelerating to the target range and will keep it there also.
Yeah, exactly. It tries to keep the RPMs of the motor as long as there is power.
Okay.
Yeah.
And you will not provide too much power so that I still have fingers then.
Probably you will have the fingers.
Okay.
And independently when it's going up or down, it will keep the speed.
It will keep the speed. It will even brake, but it's hard to simulate without the car.
Yeah, sure.
But I will try to
Yeah. So we are changing here the setting to normal. And flash it. The speed can then be set on the display.
Yeah. So
So
Georg, you can set the adaptive cruise control speed, yeah.
So I will do so, yes. I will increase it a bit more.
Yeah.
So faster than more fun. And but maybe we have it a bit slower so that we see a few things. And I can now work. I can work against it.
It's always more healthy.
But I can change the force that is there. I have to cool down the fingers in between. I can change the resistance that I give, so increase the step of the hill, and it will continue to hold the speed that I have there. And yeah, just for the material change or the fingers safety, I have reduced it a bit, but I can bring it down to very much to a hot area.
Yeah. And now we are in a real motor case, yeah. So this would be how it would work in a vehicle at the end. But we would land in this kind of full control cycle, including a velocity regulator. And again, just remember, because its motor control is to a certain extent software development, so you see all these algorithms and control tactics, they are developed in a PC, as you see. They are based on a software library, they are flashed into this computer, and is working according to the cycles which we have slowly built up together with Maximilian and Georg.